I will introduce you Yann Klinger. Yann Klinger, let me see, because it's a name that I have to read. He's director of the research at CNRS in Paris, and this is also he's part of the tectonic team at Institut de Physique du Globe, and this is also part of the university, so it's all the things together. His lab is in a mixed way there, so university and CNRS. I am very happy to have him here because he's somebody that is very interested on the process of earthquakes from many points of view. So he is pushing many keys on this aspect, on this process. And he has a background, he's a physician, but now he's almost a geologist. He's a geologist, I would say, like Paula. Where is Paula? That is an engineering geologist, and now she feels like a geologist because they have been working in geology a lot. He's very interested on the earthquakes, on the process, on how it works from the one cycle. So he has been going into earthquake places just after the earthquake to see what happened there, to see how the surface was deformed by the earthquake, by the fault moving. But also he's interested on the addition of many of these processes, no? So the effects of many earthquakes on the landscape and on the geology. So he's doing from rock mechanics to paleoseismology and active tectonics. And I'm very happy to have him here because I'm very grateful because he was around Barcelona in a leisure time, in vacation, and he offered himself, if you want, I can come. And I said, of course we want. So thank you very much, Yann. I think that's your time now. I won't be long.
Okay, thank you, Eulalia. Thank you, everybody, and to be here. So I'll try to use this thing. And as Eulalia said, I guess most of my work today is to work about the surface structure of earthquakes. And so I'll start with, maybe there is a way to get rid of the lights. Okay, it's kind of tricky. I need to point here to have the pointer over there, so it's okay. I'll just, so I want to point to this thing here, which is a surface structure. And this is a place in China somewhere, and this place has ruptured in 1931, and we still see it very well, okay, in the landscape. And probably what we see here well is that the surface ruptures are not simple. They are in fact complex features, and in fact earthquake ruptures are complex features. And it's not designed for this, but we can see here the main rupture, but we also have branches and things like this. And in fact, this is bringing a lot of information which has been quite overlooked so far. Also, we can learn a lot about earthquakes processes through this kind of information. So I'll try to take you. Now I need to move to the, maybe this way. So the thing is not working. No worries, no worries. Okay. I'll try to take you across different little tours and places to show you how we can use this kind of information. So the first things I want to mention is that indeed surface ruptures are complex. Okay, you have a couple of examples here. So on the upper left, you have a view of the Bolnai earthquake rupture, 1905. It's in Mongolia, it's where we met, in fact. And you can see that here the rupture is not one rupture, it's two ruptures going parallel for several kilometers, which should be forbidden considering stress shadows, but in fact it happens, so it's possible. You also see on this picture that rupture can be very well localized. On the right-hand side here, you have another rupture, again, strike slip. You will see I'm a strike slip guy, okay? And here what we see 4 meters of offset, but the rupture is not localized. In fact, the deformation is straddling an area of 40 meters, so distributed deformation. The last piece here, thank you very much. The last piece here on the lower left, okay, is a view of the Kaikoura earthquakes. Again, strike slip, magnitude 7.8. I'm mostly talking about big guys. And what we see here, we see again a complex ruptures. And we see here we have a little jog with some lakes. So indeed, this lake has been helped by the local farmers, but still it conveys a message. If the people choose to pick a lake here, it's because we had a basin. And if we have a basin, it means this extensional jog is not only one earthquake sphinx, it's repeating itself through the time. So this earthquake is impacting the landscape. And so it tells us that this jog is probably not only a superficial feature, it's somewhere at depth also existing and controlling the landscape. So maybe there is something to learn about fault rupture and fault structure there. So just to summarize, how much of this complexity is relevant to understand earthquakes? How we go from what Lallier or myself, or maybe many of you go in the field and come back very proudly with their super detailed map of the rupture and start to talk with their geophysicist friends, which were me at my beginning, in fact, and say, oh, what I need is this. Okay, so forget about all your details. So what I'm working on right now is try to find this right balance and convince some of our friends that maybe there is a midway somewhere which could be useful. So fault geometry matters. I just show you one example here. We are in California. So for those of you who recognize, this is the Bay of Los Angeles here. I'll try this one. Yes, okay. We have the San Andreas Fault here with the big, no, that doesn't work. With the big branch here with the San Jacinto Fault going to the south. We know we had a big earthquake in 1812, but what we don't know is, in fact, which piece of the fault broke. And so Luxos just did try some models, and the only thing I want to show through those models is that depending where you start the earthquake, on one side or in the middle, or on one branch or the other branch, you will change the final product, the final ground motion, for example, the final displacement. Maybe from your seat, you feel like all those simulations show the same stuff, but if you look in detail, surface rupture and surface deformation will be changed by 25%. If you have your house, 25% is a lot, okay? So depending where you start your earthquakes and the way it propagates, according to geometry, the end result will be very different. So we need to include this fault geometry inside our models. Okay, so today what I want to do is to address two things: combining surface mechanics, surface rupture mechanics, imagery, also remote sensing. I want to talk about slip distribution and damage, and also maybe to zoom out a little bit and talk about fault segmentation and geometry of the fault in more general way. And so to do this, I'll take you on several little trips around the world in places where we've been working with my students. And we can start with Mongolia. So Mongolia, you all know where it is. It's at the very end of the collision between India and Eurasia. So not much is happening really there, but still last century, we had 4 magnitude 8 in about 50 years. So it was quite active at that time. And so we can focus on the 1905 sequence up north there. Why working there? First, you have no problem of anthropization, like in Barcelona, for example. You see it's a quite open land. Also, it's all permafrost. It means it's all frozen. So you have pretty much no erosion. So as you can see here, the surface rupture is still super clean like yesterday. You can go and study. And in fact, you also see a lot of this secondary deformation, like this little secondary antithetic normal fault here, which is blocking the drainage. This guy has 1 century, but it's still very well preserved. And so you can document these kind of things. So we can really come and look at the surface deformation. Indeed, this rupture is 300 kilometers long, so you're not going to walk the entire thing. So in addition to field work, you also use satellite imagery. And okay, you've been spoiled now, we all use Google Earth, but we should take advantage of these high resolution images. This is Pleiad images. So you all have access through the European channel. And this is 50 centimeters pixel size. Okay, so you lost your keys, you buy an image, you find your keys. You can see on those images many drainages which are disturbed by the fault. Okay, so we can measure those offset features. Some are small and related to 1905 offset, like this 6 meters offset. Some are cumulated offset, which are like 37 here, 21 here. So meaning several earthquakes. And we can cross-check in the field, but you see, in fact, in the field, the landscape is very smooth here. It's not so easy to make an accurate measurements, while on the images, you do a pretty good measurements. So combining this imagery and this field survey really help having a good slip distribution, for example. Something else we can look with those images. So again, we are along the Bolnai rupture. We have at the top panel a piece of the Pleiad imagery. The rupture was coming from the left-hand side and would cross all over the screen. We see we have a little kink. On the middle panel, you have the map of the surface trace plus a little bit of topography. What we see that when the rupture came from left, we have an offset like 5-ish in terms of value, 4.75. And when we get into this kink, we lose steam. We get 3 meters, 3.8, 3 again. And then we get out of the kink, we start to rise again, 5, 6, and again, full steam here. So we might think that we're in fact losing some of the deformation in the kink. But if we look carefully at the top of the satellite imagery, you can, I'll try again. Like here, we can see some deformation, which is in fact thrust deformation. So no mystery here. We have this kink which produce a pressure ridge, a push-up. We can see in fact cumulative deformation in the middle. So part of the deformation that was accommodated through strike slip now moved to thrust in the kink. And if we do the total budget, maybe we don't lose so much of the deformation. If we do profile across the thrust, again, we can see here in the lower panel that we have the little scarp. And if we look at details, we see, okay, we have the 1905 scarp, but we also have cumulative deformation here. So again, the main message here is this kink is not a one-shot thing. This kink is permanent, it's part of the full structure, and it's repeating at least over several earthquake cycle, producing this complex geometry. So using this kind of information, come on, okay. At the end, we can map the entire rupture. So again, first earthquakes of this sequence, Tetzel leg rupture, started on this major branch here. And about 14 days later, we have the second earthquake that starts on the west here and unzips the entire rupture for about 300 kilometers. You can check the kilometers here. And so using the satellite imagery, we can build the slip distribution here for these earthquakes. So here, this is distance along the epicenter for the x-axis and horizontal deformation on the y-axis here. So what you can see from this slip distribution is that the average slip is about 6 meters. It's a very nice and well-behaved slip distribution. We can already feel from this slip distribution that we have, on average, a bit less slip on the western side compared to the eastern side here. And this, as you can guess, we don't like it so much, okay? Because the idea is if we get more slip on the eastern side, at some point, we need to compensate on the western side. So then mapping the details is important because on the western side, in fact, as you can see, all those yellow places are places where we can map secondary deformation. This little guy I was pointing before. Okay, so on the western end, we have a lot of secondary deformation. In fact, this secondary deformation in some places is large enough that we can quantify the slip. So those points here. And so those guys, which are almost 2 meters here, are in fact making the difference with the western side here. So it's not so much that we have less slip here on the western side compared to the eastern side. It's more we have better localized slip on the eastern side, while we have more of the distributed deformation on the western side here. Okay, so indeed, the next question is why we have this kind of feature. And so also, unlike you think I'm not a geologist, okay? I'm a geophysicist, but I can still use the geologic map. I don't understand it very well, but what I understand is that on the western side, we have plenty of different color patches, which probably shows that we have different kind of rocks, while on the eastern side, it's all green, which means one unit. And so the way we interpret these things here is that the rupture had to go through a complex medium here, find its way between units, probably going through joints which are not well oriented and generate a lot of distributed deformation. While on the western side here, it's much easier. We just clean cut through one big unit. And so we localized deformation here. So even for people like me, like a yellow geologist, okay, using the general pattern of the geology here brings information to understand why we distribute deformation differently on the western side and the eastern side here. Okay, so this was a little part of the story here. Okay, so we talk about one earthquake's deformation. Now we want to expand our record to several earthquakes deformation. You mentioned about earthquake cycle. So to do this, what I propose is we move south. This is the Gobi Altai earthquakes, still Mongolia, 1957. What is nice about these earthquakes is that right after the earthquake, the Russians, they flew over the rupture and they took air photos. So we have a full collection of nice air photos with fresh ruptures. And we can use this kind of data to measure offsets again. So I'm not going to do it again, but I'm sure you're quite familiar with these kind of things. You pick a river like, well, that's not going to work. Huh? Let's say, okay, this guy, you see it's well offset. You can backslip it and measure. And so this is a super good quality, and this is a lower quality. So you can rank those things. At the end, again, you can measure many offsets along this rupture. So this is all the data we could collect along that rupture. You have about 1,000 points here. It's not very well ordered. If you want to say something about rupture, it's a bit difficult. So you have to trick the system. So how do we do? First, we need to make a super big assumption. We have to cut our ruptures in several sections, which are probably related to geometrical asperities like bend, jogs, things like this. And we make the assumption that in one section here, for one earthquake, the slip can be averaged to one value. So this is a very big assumption. The other thing we do is instead of taking one measurement and error bar, we turn it into a probability distribution, which means we have a peak of probability, our best measurements, and then we have the lower probability to incorporate the uncertainties. So for a section like this, we turn all those data points into this forest of probabilities. Then we can sum to have a cumulative probability distribution here. And from the peak of this distribution here, we want to get the average slip for that section. And to do this, we take this one and we decompose it in a family of Gaussians. Again, we have this strong assumption. For one section, we can say the slip could be averaged by a Gaussian. So this is what you have on the top part here. The best Gaussian that would fit the highest peak. This is a green one. This is a slip of the most recent earthquake. Then you can remove it from your cumulative function. You're left with the red curve here that you fit a new Gaussian. That would be the penultimate earthquakes. You remove it, you fit with a third Gaussian that would be your pre-penultimate earthquakes, and so on. At the end, for each section, you can decompose your cumulative probability density function with a series of Gaussian. Each peak would be the slip for the first earthquakes, the second earthquake, the third earthquake, and so on. Probably not putting too much trust in here. If you do this for all those sections, well, you see in some places, in fact, you get really only one peak, but in some places, you can get several peaks that will tell you stuff about earthquakes in the past. So now we have a way to tag each of these measurements and to say this measurement was connected with the most recent earthquakes in blue, the penultimate earthquakes in red, the third earthquakes in time, the green, and so on. And it starts to be really interesting because indeed we get the slip distribution for those big earthquakes, but we see that in places where fault sections are very linear, very simple, this seems to repeat. Okay, so this pushes us toward characteristic slip, which in terms of hazard assessment is very interesting indeed, because we can start to say you need to be prepared for that amount of slip at this location. Okay, so here, even it was looking very messy at the beginning, we can say something about slip and cumulative slip. So indeed, this is not the only place we have a characteristic slip. So just to reassure you that we're not getting something out of the hat without any backup. Few other examples here. Probably the first example, Superstition Hill, 1987. They had these measurements of the slip distribution, and they noted that already the bushes were offsetted several times the 1987 ruptures. San Jacinto, California, San Andreas with the LiDAR data, 5 earthquakes, the same kind of slip. North Anatolian fault, not that clean, but maybe. And again, a big Mongolia earthquake, the Fuyun earthquake, which we worked, and this is the introduction photo. And you see we have 1, 2, 3, maybe 4, maybe 5 earthquakes with the same kind of slip here. So characteristic slip exists, very likely, if you look carefully and if you are clear on your assumptions, it's saying, okay, I'm taking clean section of the fault with simple geometry, then I can probably use this to work on the hazard part. Okay. So this is great. This is for past earthquakes, but now, in fact, we know that the deformation is not that simple, and we need to try to improve a little bit. So we want to use imagery. And so this is another part of the globe. In fact, this is in Balochistan, Pakistan. If you remember, we had a big earthquake in 2013. This is an image taken before the earthquake. So anyone wants to point the location of the fault here? It's not that easy, okay? So I see you have propositions, but probably it's much easier right after. Okay, now we have no problem, and we can see offset feature here, like we have 9 meters of offset right here. So we can really see, I'm not sure it's working, yes. Okay, we can play, I like to play, in fact. And we see it, and we can do this kind of measurements. In fact, if we can play with our eyes, probably we can teach a computer to do the same, okay? And to do it in a more efficient way. So this is what I'm going to show you now. So just, okay, the mapping, we see it's a bit complex. And in fact, we also see we have off-fault deformation here. We can feel, but very hard to measure in the field. Okay, even you are super good. We had this conversation with Eulalia before. You go in the field, what do you measure here? Okay, there is nothing to measure. Also, we see the deformation. So what we've been developing over the years, and we are not the only one, okay, but probably we are the best one, is an optical image correlation tool. By the way, this is open, so you can download and play with it. I'm not going to talk about the techniques today, but just to get the sense how it works, you have image before the earthquake or before your landslide or before your volcano, whatever. Then you have deformation during the earthquake, and you take a second image post-event. And so assuming that you can correct all the little things that the satellite will do differently, like moving like this or like that, the sensor is not exactly the same. Okay, all the cooking we do in geophysics. At the end, the only difference between your two images should be the motion of the ground surface in the horizontal motion. Okay, so I should be able, using those two images, to measure the horizontal motion of the ground for every single pixel. So if you have a high resolution image, then you have a high resolution, very dense grid of deformation. Okay, this is done by correlation, but again, we can talk about technique really if you're interested. So I'll show you one example, the Ridgecrest earthquake that you probably all know about. So this earthquake is the most recent earthquakes in Southern California, very complex, many aftershocks. In fact, a nice foreshock that ruptured before the main shock here. What I would like to emphasize here is, look at this image. This is again surface rupture. I guess we would all be able to measure the main deformation because the road is offset. Okay, this is where we would go and measure. But what about all those little cracks everywhere? They bear some deformation, okay? But again, very hard to measure because there is no offset features, or it would be too small, or you will spend your entire career just walking this path. Okay, so okay, it's a nice career, but it's quite limited in focus. So we need to find another way. In addition, this is the US, so we are on a military base and you cannot access. Okay, so we need to find another way. So if we use this image correlation and we use Pleiad images, we can produce those two fields of deformation, horizontal deformation. This is east-west deformations on the left, north-south deformation on the right. And each pixel here is 50 centimeters, independent measurement. So you have a lot of data here in terms of deformation. And you see, this is the field mapping in black. You see how we see really well the discontinuities of the deformation thanks to the image correlation. What we see in addition that you would not be able to measure in the field, for example, for those two profiles, you have the profile here, A prime on the upper part. There you see how we have a sharp step, which means deformation is well localized. But on the profile B prime, in addition to crossing those localized deformation, we have this gradient of deformation that we see in the profile, and we can measure the amount of deformation related to this off-fold deformation. The thing that you would like to measure, but you're not able to measure in the field. Right now, we can start to quantify this kind of thing. So with this, indeed, we can do a lot of measurements, but really, it's a new way of looking at earthquakes and to understand how the budget of deformation is spent along the rupture here. So just to give you a few details, okay, we're not diving too much into the ridgecrest, but you have examples of zoom here on the upper left. You see the discontinuities. We see all the little branches. You can also see the southwest, northeast kind of lines, which are in fact deformation related to the foreshocks. Very small deformation, but we can start to measure here and do profiles. If we do profiles, for example, across this small basin here, where we have distributed deformation here, several strands, this is what we have on the lower right. Again, distance along the profile. This is offset, and we have localized deformation, and we have distributed deformation, okay? So we can start to integrate this amount of deformation into our total slip distribution. So at the end, we can try to put all this together. So on this big plot here, you have, as usual, distance along the rupture here, offset on the y-axis. The small dots here are the field measurements. So people who spend days in the field under the heat and no bar and difficult in military helmets, everything, okay? But they say they enjoy, yeah? But okay, so this is their measurements. Then we can do the measurements of the localized deformation. This is the bold line colors. So this is the deformation on faults. And the black bold line is the total deformation across the entire rupture. And so the gray, which is the difference between the sum of the colored and the total, is the distributed deformation. So you can see that at the heart, at the core of the offset of the earthquake, most of the deformation is localized. But when you go to both extremities, we can have up to 30 to 40% of the deformation, which is in fact totally diffuse, totally distributed, that you would not be able to measure in the field. So this is a lot of deformation, okay, that we cannot account if we go in the field, not even talking about people doing trenches, right? Because they don't see this. So this is another issue we're not going to talk today, but we should keep it in mind. But here, okay, we have a lot of deformation which is not accounted by the field people. So this is interesting because, you know, the colleagues who do slip inversion, for example, using INSAR or Seismo, they keep talking about the slip deficit. What is the slip deficit? The slip deficit is the lack of slip close to the surface when you do this kind of inversion. So you will find many things in the literature, like we need creep, we need other earthquakes, we need post-seismic deformation, we need after slip, all this to explain this slip deficit. In fact, we don't see creep. Post-seismic, after slip are too small. And if you want to accommodate 1 or 2 meters of missing slip here, you would need quite a large size earthquakes in addition. So that would not work so much. So maybe there is something else. And so if we, in fact, do this kind of inversion using optical images to constrain the slip at the surface, which is not possible with INSAR or GPS, we get a different story here. Okay, so this is, yes, the slip deficit. Okay, so this is depth, this is a slip, and you see that if you do inversion here, we have this missing slip close to the surface, the difference between here and what's happening to the surface. So what is interesting here, I hope, yes, okay, is that in fact, if we start to introduce all our diffuse deformation, we make up for the missing slip. So we don't need the creep anymore, we don't need the after slip, we don't need the extra earthquake, we just need to incorporate this diffuse deformation into the budget, and then the slip deficit shrink a lot. Okay, so pretty much what we're saying here is that this slip deficit is mostly an artifact of inversion because our colleague modelers live in an elastic world and the Earth is not elastic, at least not next to the surface. Okay, so this is interesting. And again, it's important because in terms of hazard, then we don't have to worry so much about this missing slip. Okay, in fact, we can talk about the damage for 1 more minute. And for this, we shift to another field work, which is in fact a lab work. It's a sandbox experiment where we just do strike slip and we do image correlation, exactly the same as for earthquakes, but with regular cameras. And so we can look how the deformation is distributed in those experiments. It's partly localized and it's partly distributed here. And so we found a way to just measure those things. So again, this is a distance and slip, exactly the same as for earthquake. So here you have just a series of images from our experiment where you see the incipient fault, which is growing and getting more, I don't really like this word, but mature or more organized at least, with a nice tri-slip fault here. And at each step, we can take those photos and try to see how slip would distribute around the structure here. What we see here, so here you have the full story where you start from nothing, pristine crust. It doesn't exist in real, but okay, this is experiments. And then you start to shear and you see how the folds start to organize to end up with a well-organized structure here. So 2 things I would like you to note. First, on the right side here, you have the amount of off-fold deformation, the blue curve. Indeed, at the beginning, it's 100%. And when the structures start to collapse and to localize, we get down to 25%, like at 52 millimeter. But then we stick to 25%. You can run your fold for a long time. You're not improving your localization anymore, which means that it's probably true in real as well. Folds don't get smoother and smoother forever. At some point, you get a level where you keep having some distributed deformation. Something else which is interesting here, when we form this fold, you can see the green boxes here, they point to some asperities in the fault line, which in fact correspond to the initial position of those riddle cracks, which means even in the sand, the initial geometry of the crack will stay stuck in the blueprint of the fault until the end. Okay, so this segmentation, okay, I said the word, this segmentation will stay all the way to the end of life of this fault. Okay, and so we can, again, do such kind of, this is the same, you have one experiment, you input more and more slip, you see how the off-fold deformation decreases drastically when you start to localize, but at some point, we keep this level of complexity in the fault zone, even if we continue to move on more and more cumulative deformation, which would mean in a way that maturity here doesn't make more sense because you keep having some complexities. Okay, so this is just two examples, and you can play with different sand and different thickness, and you always get the same images here. Somehow you keep some damage. Okay, let's try to move a little bit to something different. Back to New Zealand for a minute. How can we use those new techniques to say something about earthquakes? So you probably remember these earthquakes was coined as the most complex ever until the next one, earthquake. Okay, so it started here, do this weird loop, arrive here, and then many options on the carpet. Some people say, okay, this rupture jumped all the way to this and propagated northward. Some people say, well, in fact, here it went to the subduction, traveled along the subduction plane, come back up here. Some people say, well, maybe it propagated at sea here and connect to this guy here. So we thought maybe we can bring something here. So we focused on this area and we looked at the deformation at this junction point here. So again, we did optical correlation with spot imagery in that case. So it's a little bit less resolve. You see the T shape. On the upper part here, you see the the Kekerengu fault, which is super well localized. You can see profile K1, K2, which are here. 11 meters of offset, 8 meters. It's a big offset, but super well localized. Same on the Jordan fault, globally well localized. On the Papatea fault, the story is a bit different. Again, we have very large offsets, several meters, but more distributed. Okay, you see here 3 kilometers, 2, 1, 2. Okay, so it's broader zone of deformation. So this is information we would like to use to say something about the way the rupture propagated. So to do this, we built a little numerical model where we reproduce the geometry. Again, we're not talking about techniques here, but whatever, we have this model of the rupture and we're going to propagate dynamic ruptures and see what's happening. The only interesting trick in this model is that in addition to the main fault, we open the possibility to rupture micro cracks around the main fault, so to mimic damage. Okay, so this will be an observation. So we use this model and we're going to test some scenarios. So first we're going to test a scenario where we start the rupture on this Jordan fault and see how it goes. So I hope it will work. I'm sure it will work, but okay, so you see the rupture. It's a bit dark, I'm sorry, but you see how it goes close to the triple junction, start something here. The yellow are the damage here. So you also see the location of the damage. And you see mostly the rupture propagating northward along the Kekerengu fault. Okay, so yes, it's starting again. Really something which is interesting is to see the rupture front start here and dies. Okay, so no way to rupture this part here. So this is not very good for our fault model here. So we can try something else. We can try to initiate the rupture on that branch. So this actual position is totally random. Okay, it can be any place here and just try to see how it goes. Okay. Yes, so this time it goes towards the triple junction. A lot of damage in the triple junction. And then you see how it triggers a bilateral rupture in that case. So at the end here, we are really rupturing this section and the two big faults, which we know they all have ruptured. And in addition, we generate a lot of damage in the cross section here. Okay, so we can just have one more look. So indeed, for those models, we can also compute the finite deformation of the ground after the rupture propagates. And so we can compare with our own measurements. So this is for the Jordan model. We have this is the output of the model, and we can look at the profile. So for the Kekerengu and Jordan fault, you have the blue, the data, red is the prediction from the model. Looks nice. Now, if we look at profile along the Papatea fault, we see that not even the shape is correct. Okay, so our prediction with a rupture starting on the Georgian fault, so for a rupture starting here, would not produce deformation in any way compatible with observations. If we look at the other scenario where we start on the Papatea fault, again, on that guy and the Kekarengu, we can do a good job. This is not super difficult. But in addition, along the Papatea fault itself, okay, it's maybe not fully perfect, but the shape and the amplitude is quite okay. And so this is a good argument to say this is more likely that the rupture went up north here and rupture triggered a bilateral rupture here. Okay, so we are happy. We're using our image correlation to decide between scenario. But because I'm still a field person, somehow I need to justify my trip to New Zealand. I went to walk along the rupture here. And so you have a little field photo up there on the upper left. And what do we see on this upper left? We see the scarp, okay, the main scarp, but we also see a lot of extensional cracks, only on one side, in fact. We only see on the upper side, and the location of those extensional cracks is in fact very compatible with a rupture, a left lateral rupture that would propagate northward and having extension lobe here, dynamic stress, only on that side. And only on that side would be only on the extensional side we see in the field. So in fact, this little observation here is one more proof that very likely the rupture went up there this way. So at the end, we can really propose that the rupture did this kind of things, and when at sea, did this little jog here, which is not that big, get to this intersection, and then propagate bilateral, which, by the way, is very much like the Turkish earthquakes of 2 weeks ago. Okay, so here is a nice way to join this optical and field data. Okay, I need to move on. Let's try to zoom out a little bit to finish and try to say something about fault structure. So if we want to talk about segmentation and fault structure, we need data, okay? We don't have so many, and we see that the quality of surface rupture maps is very variable in the literature. We, in fact, have very little data. But we would like to say something about segmentation from those data. So to do this, we put together a little tool. Let's say you come back from your Landers mapping, okay, super proud. It was not too difficult, in fact, okay? You could see all of you, I'm sure. This is a bit too complex, so you simplify to only keep the piece of the rupture that, in fact, bear real slip. And from this, you want to decide how to do some segmentation, how to cut this rupture in pieces that you can discuss with your colleagues and not only argue, but say, okay, we agree this is the way to cut it. So to do this, yes, I thought I had one more slide, but it's okay. We put together a little, how to say, Misfit calculation, where we would explore how many segments we need to approximate this surface rupture with straight lines. Okay, so very simple. You digitize your thing. You can do the perfect match with many small lines, super match, but very useless. Or you can say, okay, this is only one straight line, not very useful as well. And so you can explore the number of straight lines and where to put the boundaries to make a decent fit. In that case, you can show that with 4 segments, you do a fit, which is very okay. If you go for less, you really have your misfit function that totally explode. Okay, so you have now a tool that you can share with your colleagues, even with your colleagues geophysicists. They can play with it and they'll have to agree with you, okay? So at the end, you can take all your collection of earthquakes. You look at the surface rupture. You see here you have earthquakes from California, from Asia, from Iran. Something which is interesting, you have the total geological offset attached to each fault, which is somehow a proxy of the age of the fault, okay? Large cumulative offset should be equal to old fault. So many different ages. And we do this little calculation, and we end up with this plot where you have the total rupture length and the number of segments. So each of these points is one earthquake. For example, Landers, which has a rupture which is about 70 kilometers long. You can approximate the rupture with about 4 segments, plus or minus. And then you have your collection of earthquakes. And so what is really interesting here is that all those nice continental strike slip, they're super well behaved. You can approximate all those points with one straight line, and the slope of this straight line is the average length of one segment. Okay? So what this figure says, it says that for all strike slip earthquakes, everywhere in continental setting, you can divide your surface rupture in segments which length on average will be about 17 kilometer long. It works in California, it works in Asia. So in California, it would probably be a bit more smaller size, like 12, 15. In Asia, it will be a bit longer because we have a big craton, more like 20, but okay, let's say 15 plus or minus 5, we are happy. We're not done with our geophysicist friends, okay? We need to convince them more, so we just do a little swing by seismology. Probably you recognize this. This is a kinematic inversion figure. So x-axis is distance, y-axis is depth, color coding is slip, and this is done with INSAR or Seismo or whatever. Seismologists are super well organized, so they have a database. You can dig a lot of those, and it's very easy to measure the size of the main patch of slip just based on gradient. Okay, so again, something you can reproduce easily. So in that case, for example, okay, forget about the details. We know they don't have the resolution, but the big patch would be about 20, 21 kilometers. So you can use the entire data set. I'm sorry, this figure is a bit old. And look how this patch is growing when you grow magnitude. And so indeed, when you grow magnitude, the patch is growing, growing, growing to some extent, where around 7 plus, you saturate. Okay? It means that at some point here, instead of keeping growing your patch of source, you will generate a second sub-event, a third sub-event, and so on. What I call, like, instead of having a French fries kind of things, you have a potato chips source. So this is what we have here. Okay, so 25 kilometers. So these 25 kilometers, I think, is about the same as 17, roughly, plus or minus the uncertainty. We are in the same range. Okay, and so here now from field and seismology, we can advocate that our segmentation is 15 to 20 kilometers long, everywhere on continents. And this would be, in fact, consistent with the thickness of the brittle crust. So now we have something that seems to be independent of total fault offset. So forget about the maturity for this. You have a physical base. This is just a first order scaling with the crust, and is valid everywhere on continents on the planet. It's not depending on your tectonic setting. So now when you talk about segments, please talk about something which is 15 to 20 kilometers. Anything else, call it whatever, fold, section, I don't care. Okay, so just to finish, I want to show you a few things we are testing now to push this a bit further and to test it. And to do this, we back to the lab. So first thing we could do is to use sandbox, because sandbox it's very easy to change the thickness of the sand. And if we are not too wrong, the distance or the length of the segmentation should increase with the thickness of the sand. Well, it's working nicely. Okay, and so the idea we have here is that when we do shear in experiment, we will first create those riddle shears. But at the end, what matters is this distance here, which will be the actual shear in between the riddles, and this will be your segments. Okay, so we measure this distance here. And it seems to work. So here, what we have the earthquakes I mentioned before. Here we have the ratio between segment length and the brittle of the crust for those earthquakes, for example. And this is our sand experiments. And you see that, in fact, the ratio between segment length and brittle and thickness of the brittle material is the same for the sand and for the Earth's crust. So it seems to be a very general behavior for any brittle deformation. We can try to push it a little bit more. So we move to numerical modeling. So this is just a sandbox, but a numerical sandbox. Okay, so we have 1 million pieces of sand here, and we can shear along this discontinuity and see what's happening. Again, we can change the thickness of the box. You see that when we change the thickness of the box, we change the distance between the riddles. So again, but this we knew now, but it's always happy to see it's working. But this is more interesting. Now we look at a section. Okay, we see the cracks. When we start to shear, each of these points is a little crack propagating through the system. Now I need to try something. Okay. Yeah, that's not so easy. Huh? Okay. I'll try something. Okay. So when we start to shear at the beginning, as you can feel, the cracks will grow from the base of the box. Okay, growing uphill. A box here. This is boundary effect. But when we continue to shear, something different will start to happen. So let's cracks grow. Let's grow towards the top of the box. Okay. Okay, and now we have something different that starts to happen. Okay. We have also cracks that start to generate at the top of the box, okay, independently. But with a big difference from the bottom, where you have cracks everywhere. At the top of the cracks, they are clustered. Okay, we have specific location where we have the cracks. In between, no cracks. Okay, so we have a spatial pattern here. And so we can see how this spatial pattern is in fact developing downward. At some point, it will connect with the cracks coming from the top, and we will generate our riddle shear with this specific spatial pattern. Okay, so we can reproduce this specific pattern here, which was a bit unexpected. Okay. No. Okay. So if we put this again in a numerical model, we have the shear at the base. We have the riddle, which are indicated here. And what we did is we computed the stress on the segment plane. Okay, this blue surface here. And we can test the effect on the stress of the ratio between the length and the height. Again, the length of the segment versus the thickness of the material. If we have a ratio of 1:1, we see that in fact the top of the model here is controlled mostly by compressional stress, okay, which is what we have at the surface of the Earth. This is why it's not crumbling, because compression is hard to break. If you start to make this longer, so change the ratio, in fact, because you're shearing at the base, you increase tension, and at some point, tension starts to dominate at the top of the model. And if you start to pull, what's happening? Well, it breaks. Okay, it's very easy to break in tension. So at this stage, if you break here, well, you change the ratio, you're back here. Okay, because now we're 1.5, we cut here, it means 11/10, we're back here, compression stable. So we have this loop here. Each time this ratio starts to be too close to this value, we need to make one more break to get back into stable state. So at the end, we're almost at the end of the story here, because now we have our numerical modeling, our sandbox, our earthquakes data, always a ratio between length of segments and thickness of the material. We see that they all obey the same value. And in fact, they all point to this ratio about 1:1.2, which is a stable ratio. If you make a ratio which is larger, we get to tension dominating the cracks, the surface, sorry, and we crack, and we need to bring back the system into the stable position. So we have here a nice little physical process to explain why we see this in nature why we see this in the sandbox, why we see this in the numerical model, why we see this in a piece of concrete. In fact, it's everywhere you break a piece of solid material, it will obey this kind of stuff. Okay, so just to finish, few take-home messages. So damage and secondary faulting, they are important. It's good to look at them, especially if you're interested in hazard assessment. Even you're not a geologist, it's good to talk with your geologist friends, okay? There is something to learn from them. And strike slip fault, okay, we all knew they were segmented, but now it takes a new meaning, I hope. And we can say, okay, segmentation probably relate to the thickness of the brittle crust. Earthquakes can rupture a series of segments, okay? It's just the brick to build the house. In fact, the brick that will be destroyed by the earthquake. Okay, and we can even think about using this as a new metric when we built our synthetic catalogs of earthquakes. So this is a new piece to think about it. And I think it's way long enough, so I'll stop here. Thank you.
Thank you, and you gave us a lot of things to think at. A lot, maybe too much. I'm sure there must be some questions. Jaume.
Thank you very much, Yann. I really liked your talk, especially the segmentation and the distribution of the segmentation. But if I am not wrong, I think that most of the examples you were showing were strike slip faults.
Yes.
So can you do the same thing with normal faults, extensional faults, and with thrust?
Okay. First, you're right. I'm a strike slip person. I work 2D. Yeah? Okay, I take the easy part. I left to use the hard part. But I think, yes, probably it would be possible. In fact, we tried. But there is this complication with all the deep slip, which is not really 2D. Okay, you have to account for the deep. Then where do you go? Where do you stop? It starts to be really difficult. But still, if you look at normal fault, for example, in places which are a bit more understood and where we don't have too much inheritance, like AFR, I mean, those volcanic areas pretty much, you still have a very nice scaling, okay, because you have no history. I guess in Italy, it would be more complicated because you keep accumulating one structure over the other one, but I don't see why we should not have the same scaling.
And the second question, the second comment, you listed here as the second message to take home, which is the importance of the geology and the importance of the large, let's say, faults that are already there since the Barysk, and sometimes that were reused during the extension of the Mesozoic. I'm talking about Europe, let's say, but you can just go also to the Tibet.
Yeah.
And also then they are reused again as compressional structures during the collision. So I think that these points like the earthquake in Turkey, where normally this was the limit in between the Arabian plate, where the earthquake is the limit in between the Arabian plate and the Turkish block or the Anatolian block, and probably inherited structures are very important. And I think that most of the guys like you working in the earthquakes, they look very much at the surface deformation, which is where you have to work. But I think that the help of geologists can be very good too.
Yeah, it's critical, in fact. I'm quite convinced.
Thank you very much.
And I come from far. Huh? I come from hardcore seismology, so.
Thank you very much. It was really great for earthquake geologists as we, the talk, very instructive. It's maybe very basic question. When you use the insert to compare the previous and after earthquake signal, let's say, did you already detected which orientations are, let's say, feasible to, because I know that depending on the orientation of the fault and the satellite, at least with slow moving faults, we cannot. There is nothing to do. Let's say the signal, the interseismic signal cannot be measured.
Okay, so several things. First, here we don't look at interseismic signal. Okay, we only look at the big deformation.
Yes.
You mentioned about INSAR. So you're right, INSAR is looking on the side like this, and the pixels are not even squared. So there are one direction which is super good, pretty much east-west, and one direction which is pretty bad, mostly north-south, which for Spain is not so good. But for image correlation, for example, so optical image, we don't have this limitation. Okay, because you can do it with your phone camera and take 2 photos like this, it will work. Okay, so indeed, there is a lot of cooking like INSAR, like any other processing. You need to put the 2 images exactly in the same reference frame, and then you still have differences which are deformation. But in that sense, we are trying to measure interseismic deformation, for example, with this kind of optical correlation. So far, it's not working very well because still our pixels are 50 centimeters at best. We can measure like 1/10 of the size of the pixel. This is our threshold, but it's still 5 centimeters. So 5 centimeters of interseismic slip, you need to have a time long enough. Okay, so far we haven't found it.
Because the oldest pictures you are using are from when?
Well, you can find very old pictures, okay, but then the resolution will not be so good. But if you have, for example, air photos, that's probably our best hope today, is to find old air photos with low elevation. If we have still all the camera setting and all this, then maybe we could do something. Okay, but satellite imagery, well, you know Google Earth like me, it's like 10 years. Okay, 15 maybe, for high resolution. Spot imagery in the 90s, but the pixel is 10 meters, so you will never see 5 centimeters.
But our slip rates here are very low, but maybe we should try it at least.
Yeah.
And regarding the secondary faulting, so for instance, if there is an earthquake now, but we have to choose, let's say, how critical you find the mapping of this secondary faulting?
I think it's very important, okay, because especially, okay, let's take the Turkish example. Turkish example, most of the rupture you've probably seen, it's in the fields. It's going to be gone in 2 or 3 months from now. And a lot is distributed on several sections, okay? Hard to measure, but in terms of hazard and amount of slip that went, it's very important. So I think it's critical to measure, but we were discussing this with Eulalia. I love to go in the field, but for surface rupture, I think we do a much better job with imagery today. At least if we don't have trees everywhere. But even when we have trees, we have been working on the Palu earthquake in Indonesia, which is rainforest everywhere. But we can still measure the displacement pretty well. So I think imagery for this kind of work today, this is the way to go. We need to find another excuse to go in the field.
Very impressive talk. Thank you very much. Just one, you probably worked on different geology backgrounds from the images that you showed. How sensitive is the geology on these things? I mean, you've showed that everything pretty much agreed, but some of the fluctuations that you see on the measurements, have you looked at those, if they are looked in terms of geology, in terms of different domains? Are you looking at
yes,
I don't know, it's going to be different to looking at the basin, the regular basin that looking at bedrock, I guess.
Yes. So first, indeed, you're right. I mean, I try to simplify to get the big picture, but we have a lot of noise in our data, which for me is first because we have no pristine crust. Okay, it doesn't exist. We always have in heritage. So this is embedded in the way the rupture propagates. And we have been looking with colleagues like bimaterial things, so different geological units that will drive the way the rupture propagates, for example, and the way the deformation is going rather this way or that way. And we see signs, okay? So far, what we cannot do, we were hoping, for example, to say, I'll show this little example of New Zealand. It's okay, we have the extensional cracks only on one side, this is great. So the idea would be, can we use this for past earthquakes and say the earthquakes in the past were propagating this way? Well, because we have issues like the one you're pointing, like different materials and things like this, it's not that straightforward. And so far, we cannot really use it in a systematic manner. It's fun for New Zealand, it works, okay, but it's not enough just to say it went this way.
The other question I was wondering, you're actually mapping basically the brittle ductile transition just by looking at the segmentation distances, which is, I think it's a fantastic result. Is there any influence, or can you take into account the entire crustal thickness?
Well, the point is,
or can that be done?
Okay, I see what you would like to do. Yes, but because for us, as you said, this scaling is really controlled by the part which is breaking. Okay, and in fact, it's also seen in the one way to constrain this thickness is the lowest background seismicity. But below, we're changing totally behavior. We go into the more viscous stuff. I don't think we have evidence. At least I cannot think right now at some signature. So I have no good answer for this.
No, I was just thinking on the different patterns that can be seen in the Bayesian range, for example, in contrast with what you see in Mongolia.
Yes. But Bayesian range, now we shift to normal folds. Okay, so we back to question one. And in addition, we are not even sure they're deep like this or if they really get listric in this fluid material. So, but yes, I can see your point.
Any question?
Any more questions? I just wanted to ask you something, but it's more general because now, according to what you are explaining today, what do you think is the role of the geologist in an earthquake? I mean, what should we do after? We should just stay on our desks doing this analysis of different images and from that? Or is there something that you think we can still do in the field apart from mapping the rocks, not only the surface rupture, because now it's apparently it's not anymore.
I'm not going to have many friends here, and this is recorded.
Many geophysicians here.
But yes, I mean, as we discussed a bit before the talk, I think for just response after the surface rupture, again, if we are in tropical forests, it might be a bit different, but most often we should spend our time fighting with space agencies to get as much as possible coverage. That would be the main task for people like you, or at least like me. And then it would be the work of looking at the different kind of rocks and probably inheritance. I mean, for Baluchistan earthquake, I could not show today. I could speak for 3 hours, okay? But we can really see how the rupture is in fact influenced by structures which are embedded in the geology. So they are long-term structures. And we see the rupture is always trying to branch, and then it's come back and it's trying to branch. And we can really see that. And this, you really need to have the geological map to show that we have this fabric. Okay. In Ridgecrest also, there is some fabric that is influencing very strongly the rupture. This is not a geophysicist like me who will find this, okay?
So what you say is that we need really good maps, good geological maps,
exactly.
but not
exactly.
Yeah. And then the other thing that I was a little bit wondering is about what you were saying about the diffuse deformation that we cannot catch doing paleoseismology.
No.
Do you think, because on the graph that you were showing, the long term and the short term, when you were looking at the distribution of slips, those very nice graphs on different earthquakes, the long term and the short term were very similar. So do you think that we can just analyze the geological long-term signal, just like in normal faults we do topographic profiles, or we look and then extrapolate that into the short term?
I think this would be the way. Yes, you need to have something that you can average enough and far enough. This is what we all do. Okay, we do a slip rate. We go far enough to be sure we catch everything. And again, I'm not going to have many friends here, but people who do magnitude from trenches, for example, I think 90% is garbage. Okay.
From the slip prevent, let's say,
Yes, exactly.
So we
I
should
mean,
use the line.
maybe if you can do 3D trenching along strike slip, you can, but many people just do trenches across strike slip. They look at the stuff and say, oh, we do a magnitude. Forget about it.
Mostly if it's just a left lateral strike slip fault.
Yes. So it's probably a bit easier on normal fault, but I would be super careful.
Thank you. Any more questions that you have on your map?
In addition to good maps is to have good and well done cross sections at the crustal scale. I remember we work in Sierra de Piedepalo and also in the Kurdistan in Iraq, and the earthquakes that were occurring there were fitting very well the geometries of the faults we were finding according to the geology at surface and the topography. So I think that this is very important, and vice versa. From the earthquakes, you can refine very well your cross sections.
Yes.
So I think that this is very important, not only the maps.
Although we can have a change on the style also, no? So in a certain moment we change the tectonic style. So I remember in Italy we were looking at faults that were completely different from the ancient fault, from the Pleistocene faults, and in the Holocene where they were different. So but this is a step that we can avoid. Okay. So if there is no more questions, thank you very much to all of you, and thanks a lot, Yann. That was an incredible talk. So thank you.